So today we're going to go through the trig form of complex numbers. Okay. Today and tomorrow. So today we're kind of get the basics, and tomorrow we'll go further with it. Okay. So first of all, we can graph a complex number on in the complex plane. Okay. The complex plane consists of a real axis and an imaginary axis. Okay, this is not the coordinate plane we're used to seeing, because this is the complex plane where we have a real axis and an imaginary axis. Okay. Remember, a complex number is in the form real plus imaginary. Okay, back from, oh, what did we talk about imaginary numbers? I don't even remember. Was it like very beginning of first semester, I think? Okay. So in the complex plane, here we have the real axis and here we have the imaginary axis. So the number 3 plus 4i is graphed by going out 3 on the real axis and up 4 on the imaginary axis. Negative 2 plus 3i, left 2 on the real axis, up 3 on the imaginary axis. Questions so far? Negative 5i. There's not a real piece, so we don't move over on the real axis. We just go down 5 on the imaginary axis. Okay. Now, we're going to talk about the absolute value of a complex number. I believe this is something that you have seen before, but you may not remember it. Does anybody remember how to find the absolute value? Okay. What does absolute value mean? Distance from 0. Okay. So when we talk about the absolute value of 5 or negative 5, both of those have a distance of 5 from 0. How are we going to find the distance from 0? Okay. If we're talking about distance from 0, on the complex plane, we're talking about the origin, right? Okay. So the distance from 0 is going to be the length from the distance, if you will, from the point to the origin. Okay. So what we're going to do is use the Pythagorean theorem. Okay. The absolute value is our distance from origin. So what I'd like you to do, I'd like you to plot the point 3 plus 4i. Okay. Over 3 on the real axis, up 4 on the imaginary axis. So this orange dotted line that you see, that's representing the distance from the origin. We can make a nice little right triangle out of this, can't we? Okay. So to find our absolute value, we're going to use the Pythagorean theorem. Square root of 3 squared plus 4 squared. Does that look familiar? It looks like how we calculate magnitude, doesn't it? Okay. Is this a vector? No. But the length of that line segment is the same as the length of a vector. Okay. So the absolute value of 3 plus 4i is 5. That point is 5 away from the origin. Okay, let's talk about the trig form of a complex number. Okay, so let's think about what our graph looks like when we graph these on the complex plane. Okay, here's the picture I want to look at. Here is my coordinate. To plot that coordinate, we go horizontally A and vertically B, right? What does this R stand for? Okay, leave it as radius. We just found the absolute value of the number, right? The distance from the origin. Okay, and then we have the angle that hypotenuse is making. How do you think how are we going to figure out theta? Okay, if we know A and B, we can use the inverse tangent, right? Okay, here we know that the tangent of theta is B over A. So if we know A and B, we can find theta, right? Still looking familiar, isn't it? Okay. What about let's set up our other trig ratios. Okay. We know the tangent of theta is B over A. What about the sine of theta? B over R. And the cosine of theta? A over R. Okay. So if I want to write A and B, then A and B are these. A is R cosine theta, similar to the horizontal component of a vector. B is R sine theta, similar to the vertical component of a vector. These are not vectors, but how we find these things are the same. So the trig form of a complex number is this. Okay? If we have A plus BI, then we can write it as R cosine theta plus R sine theta I. Now I know this looks awkward because the I is in front of the number. They write it like that so that it doesn't look like it's in the angle here. Okay, we have the sine of theta. We're going to write it in front, and I know that's kind of awkward. If you want to write it at the end, that's fine. But in the book, they write it in the front of the R sine theta. Okay. Now I promise there is a purpose to writing our numbers like this. Okay. Eventually you'll get to see there are some shortcuts for when our complex numbers are in this form. Okay. Right now it seems kind of silly, but there will be a purpose, I promise. Okay. So let's practice writing our numbers in that form. Alright, so first of all, let's talk about what this point looks like. Negative 5 plus 6i. We're going to go negative 5 on the real axis and positive 6 on the imaginary axis. So there's our point. Okay. To write our number in trig form, we want R cosine theta and r sine theta. So we need to know what our distance from 0 is, and we need to know what our angle is. All right? So I'm going to go ahead and draw our triangle here. How do we find r? Square root of 5 squared plus 6 squared, which is what? Yep, square root of 61. Now we need this angle right here. Okay, how are we going to find the angle? Okay, so you'll want to take the inverse tangent of 6 over 5. And what does that give you? It's 50.19 degrees, the actual angle that we want. No, that's our reference angle. We're in the second quadrant. How do I get the real angle? Okay, we need to subtract this from 180. Okay. So, negative 5 plus 6i would be the same thing as square root of 61 cosine of 129.81 degrees plus I square root of 61 sine of 129.81 degrees. Well, it's not a vector. But how we found each piece up there is exactly the same as how we found each piece in the vector. Right? So the math is not different, but what it represents is different. Okay. Now, I realize that we have two different i's that we've been working with now. We have an I that's a vector and an I that's an imaginary number. Okay. My suggestion to you would be to write them differently somehow. I always italicize my imaginary number I. Okay. So I know that it's an imaginary number. Okay. Obviously, this isn't a vector because it's not. It's not written in vector form. Okay. But I know that we're working with two different i's in this chapter, so my suggestion to you would be to somehow italicize the imaginary I so you know. Okay? Now let's go the other way. I'm giving you a complex number in trig form. I want it to be written in standard form. Okay? Oh, I have an extra N in standard. I wouldn't go with that. Sorry. My fingers got happy, apparently. Okay, so how do we get this into standard form? Okay, well, first of all, yes. This is 3 cosine of 315 plus I 3 sine of 315. Can we evaluate the cosine and sine of 315? Okay. What is the cosine of 315? Not in your calculators. Thank you, Chase. Square root of 2 over 2. What's the sine of 315? So our number is 3 radical 2 over 2 minus 3 radical 2 over 2i. If it is a special unit circle angle, you are not using your calculator. Now, why are we doing this? Why do we have the trig form? Okay, there are some shortcuts to multiplication, division, and taking complex numbers to powers. Okay. So let's go ahead and look at those. Okay, so first of all, I want you to write this down. Okay, I'm giving you two general complex numbers. Okay, do you notice how the R is written outside with the parentheses? Okay, if you want to write it as R cosine theta plus I times R sine theta, you can, but all they've done here is just written it so it's factored out. If you don't like that, write it distributed in. Okay. So here are our shortcuts. Okay. If you have two complex numbers that you are multiplying, 1 plus 2i times 3 minus 2i. How do you multiply those two complex numbers like you did on your homework? What did you have to do? If I asked you to multiply those two complex numbers, what would you do? You would have to do your formula, right? Combine like terms, simplify what you can. Okay? Now, if you have two complex numbers in trig form, all you have to do is multiply your R values and add your angles. And you have your new number. So multiply the R's, add the angles. What do you think our shortcut for division will be? Divide the R's, subtract the theta. Try and move that up. Okay. I will warn you, there is a shorthand to writing these numbers, okay? Writing complex numbers out like that could get kind of tedious, right? It's a lot of things to write. A shorthand for writing the trig complex numbers out is this. If you see RCIS theta, this is what it stands for. R cosine theta plus I sine theta. That is just a shorthand to write it. And it doesn't take up as much room, but that is what it means. Okay, the C for the cosine, the I for the imaginary, the S for the sine. I'm going to do a couple of examples. Here's our first one. 4 CIS 120 times 6 CIS 315. Okay, so 4 cosine 120 plus I sine 120 times 6 cosine 315 plus I sine. Okay, if we are multiplying, what do we do with our R's? Multiply. We do the same operation with our R's that we would. So 4 times 6 is 24. What do we do with our angles? We add our angles. So what's 120 plus 315? Okay. Now, anytime you give me a number in trig form, I need that angle to be between 0 and 360. Okay? This angle is not between 0 and 360. How can we get it there? Okay, remember we have that vocabulary word coterminal angles. Okay, so they have the same values, they're just a rotation different. Okay, so if we subtract 360 to get our coterminal angle, what would that be? Good guy. So this is the answer that I want. Let's try a division problem. $15 CIS 240 divided by 3 CIS 135. Okay. What do we do with the 15 and 3? Divide them, so we get 5. What do we do with the 240 and 135? Subtract them, so what is 240 minus 135? Is that an appropriate answer? Yes, our number is between, or our angle, excuse me, is between 0 and 360. Okay, it is possible, okay, if your angle in the denominator is bigger, you're going to get a negative angle. Okay, so then you have to add 360 to get it between 0 and 360. Okay. Question. I'd like you to write down your assignment, and I want you to go out and get out your book so we can talk about a couple of problems. When you have it written down, get out your book.